On April 2, Google made an announcement that marks a significant moment in the open AI landscape. They introduced Gemma 4, which they are calling their most intelligent open models to date. This was not just another incremental release, it represented a clear statement about what OpenAI can achieve when backed by serious research resources. The launch built on something remarkable since February 2024. Developers had already downloaded the Gemma family over 400 million times. The community had created more than 100,000 variants, forming what Google calls the Gemmaverse. That kind of adoption tells you something important. Developers were hungry for capable open models, and they were finding real value in what Gemma offered. But what makes Gemma 4 different comes down to one core innovation. Google calls it intelligence per parameter. The idea is straightforward, but the execution is anything but simple. They have managed to squeeze more capability out of each parameter, meaning you can run frontier-level AI on hardware that previously could not handle such sophisticated models. This matters enormously for developers who do not have access to massive computing resources. The technology behind this breakthrough comes from the same research and engineering that powers Gemini 3. Google essentially took what they learned building their flagship proprietary models and applied those lessons to create something that can run on your laptop or even your phone. It is the kind of knowledge transfer that only happens when a company commits to both closed and open ecosystems. Perhaps most significant for the developer community is the licensing. Gemma 4 is released under Apache 2.0, a genuinely open license that gives developers complete freedom to modify, deploy, and commercialize their work. Previous versions used Google's custom Gemma license, which carried more restrictions. This shift represents a meaningful change in how Google approaches the open AI community. The 4 model sizes in the Gemma 4 family are each designed with specific hardware in mind, and understanding this hierarchy helps explain why Google structured the release this way. At the smallest end, we have what Google calls the effective models, specifically the E2B and E4B. These are built for edge devices, which means things like Android phones, Raspberry Pi boards, and Jetson Nano units. The key advantage here is that these models can run entirely offline with near zero latency. That is a big deal for applications where you need instant responses without waiting for a server somewhere, or where internet connectivity is not guaranteed. The naming convention tells you a lot about the design philosophy. The E stands for effective, and the numbers represent roughly 2 billion and 4 billion parameters respectively. But what makes these models special is not just their size. Google has optimized them specifically for the constraints of edge computing. They prioritize multimodal capabilities and low latency processing over raw parameter count. They feature native audio input for speech recognition and understanding, and they handle video and images natively. The edge models also come with a 128,000 context window, which is remarkably generous for something running on a phone. Moving up the scale, we get to the larger models that target developer workstations and accelerators. The 26 billion model uses a mixture of experts architecture, while the 31 billion model is a traditional dense model. These are designed for compute-intensive workloads where you have access to proper hardware acceleration. The larger models offer even more context capacity, up to 256,000, and they deliver what Google describes as near-frontier performance. What ties all 4 sizes together is the deliberate optimization for specific hardware overhead requirements. You pick the model that matches your deployment environment, rather than trying to shoehorn a larger model into constrained hardware or underutilizing powerful hardware with a smaller model. One of the most interesting shifts with Gemma 4 is how it handles different types of input, rather than treating images, video, and text as separate problems to solve all four models in the family process. These natively together. This matters because it changes what you can actually do with the model for images and video. Gemma 4 supports variable resolutions. What this means in practice is that the model can work with images at their full size, rather than forcing everything into a fixed dimension. If you have ever worked with vision models that compress or crop your inputs, you know how much detail gets lost. Gemma 4 preserves that information, which makes it particularly strong at tasks like OCR and chart understanding. Reading text from an image or interpreting a complex graph becomes much more reliable when the model sees the whole picture. The smaller edge models add another capability that feels genuinely useful. They accept audio input natively. This is not just speech to text layered on top. The models actually process spoken language directly, which opens up possibilities for voice interfaces. Running entirely on device. Language support has expanded significantly as well. Gemma 4 was trained on over 140 languages, which gives developers a much broader foundation for building applications that need to work globally. The training is not just a thin layer. Either the models understand context and nuance across this full language range. Context windows have grown too. The edge models offer 128,000 tokens, while the larger models extend to 256,000 for developers. This translates to something practical. You can now pass entire code repositories or long documents into a single prompt and expect the model to reason across all of that content at once. No more chunking and hoping the model remembers what came before. The benchmark numbers tell a story that honestly feels a bit hard to believe at first. The 31 billion model currently sits at number 3 on the Arena AI Text Leaderboard, which is the industry standard for ranking open models. The 26 billion model holds the number 6 spot. Think about that for a moment. These are relatively compact models, rubbing shoulders with giants at the top of a global ranking. But here is where it gets really interesting. Google is claiming these models outperform competitors that are up to 20 times their size. That means a model with roughly 30 billion parameters is going toe-to-toe with models packing hundreds of billions of parameters. And winning. This is not just about raw horsepower anymore. It is about efficiency and how cleverly the architecture is designed. When we look at specific benchmarks, the results are equally impressive. Gemma 4 delivers state-of-the-art performance in mathematics, instruction, following, and reasoning tasks. These are not fluffy metrics. Either math and reasoning benchmarks test whether a model can actually work through complex problems, step by step, not just generate plausible-sounding text. Instruction following measures whether the model does what you actually asked it to do, rather than what it thinks you might have wanted. So what does frontier-level capabilities with significantly less hardware overhead actually mean in practice? It means you can run a model that competes with the biggest players in the industry on hardware that fits in a typical developer workstation. You do not need a massive cluster of GPUs. You do not need a corporate budget just to inference the model. The intelligence per parameter metric that Google keeps mentioning is essentially a measure of how much thinking ability they have squeezed into each unit of model size, and based on these benchmarks they have squeezed quite a lot. The licensing decision Google made with Gemma 4 might actually be the most important part of this entire release, even though It is the least flashy. Previous Gemma models used Google's custom license, which came with restrictions that made legal teams nervous. Companies had to read through terms, carefully figure out what they could and could not do, and often decided the potential headaches were not worth the risk. Apache 2.0 changes that conversation entirely. Under Apache 2.0, developers can modify the model, distribute it, and use it commercially without asking permission or paying royalties. The license also includes patent protections, which matters more than people realize in the AI space. You can take Gemma 4, fine-tune it on your proprietary data, deploy it in your own infrastructure, and never send a single byte back to Google. That is what digital sovereignty actually looks like in practice. But there is a broader concern here that enterprise teams have learned to take seriously. Open model families do not always stay open. Alibaba's Qwen model family spent months building trust and adoption under permissive licensing, then shifted toward more restrictive terms. As the models gained traction, companies that had built products around Qwen suddenly found themselves in an awkward position, either accepting new limitations or freezing on older versions. That kind of bait and switch creates genuine hesitation about investing in any open model ecosystem. Google's decision to go with Apache 2.0 is a signal that they understand this fear. It is a commitment that Gemma 4 cannot be re-licensed retroactively in ways that pull the rug out from under developers. For organizations dealing with sensitive data, regulated industries, or sovereign AI initiatives, that predictability matters as much as raw model performance. You own the weights, you own the infrastructure, and you control where your data goes. The real-world applications of Gemma 4 are already taking shape in some fascinating places. In SATE, for instance, built BGGPT, which is the first Bulgarian first language model. This matters because it shows how organizations can take an open model and adapt it for specific languages and regional needs that larger commercial models often overlook. Yale University took a different approach entirely. Their Cell 2 sentence scale project uses Gemma 4 to help discover new pathways for cancer therapy. These researchers are doing work that could genuinely save lives, and they are doing it with an open model they can run and modify themselves. For enterprises, the appeal comes down to a few practical advantages. Cost efficiency is the obvious one. Running models locally means you are not paying for API calls every time you need inference. Customization matters. 2. You can fine-tune these models for your specific domain, whether that is healthcare, finance, or manufacturing. The offline operation capability is something I think a lot of people underestimate. If you are in a regulated industry or dealing with sensitive data, being able to run everything on your own hardware disconnected from the internet changes what becomes possible. Data privacy becomes a built-in feature rather than an afterthought. Chirag, Decade, an analyst at Gartner, has been advising enterprises to think about this more strategically. His guidance is that companies should not be choosing between open models and proprietary ones. Instead, they should treat AI as a portfolio. You use different tools for different jobs. But he also cautions that open models do not come with the same safety guardrails that closed systems provide. Enterprises need to build those protections themselves. It is more work upfront, but it gives you control over exactly how those safeguards function.